So everybody can hear me, I hope, and I'm very happy to be here with you today. This has been my sabbatical long project working with a not-for-profit startup called VotingWorks. And so today I'm going to be telling you, if I can share my screen. All right. So now I hope everybody can see my slides. And today I'm going to be telling you about encrypting and tabulating big elections, the design of Arlo E2E, which is the system I've been working on all year, and how Ray helped save the day. So I've used it and learned my way through a lot of different Ray features this year, and I'll be talking a little bit about voting and a lot about scalability and how to make it all come together. Okay, so my research, I'm a professor. The research that I do normally is all about vulnerabilities in electronic voting systems and how to make newer voting systems more robust, more secure. And that often involves paper, but it also involves some technology too. So today what I'm going to be talking about is an auditing mechanism that you use after the election is over to convince yourself that you have the correct winner, which, as you might imagine, is a topical challenge. Today's talk is less about the election-specific technology, although I'll give you an introduction, and it's really more about scaling up a big CPU-bound job using Ray. But I will throw in little bits of election stuff as well. So as a little bit of background, I want to introduce a concept called a risk-limiting audit. This is a random sampling process that you use when you have a universe of paper ballots that were scanned by a machine, and then you have electronic copies in the machine, and you tabulate the electronic copies, but you want to make sure that there wasn't some kind of error. That error could come from any of a variety of reasons, whether malicious or benign, but you want to make sure that the paper ballots and the electronic ballots match up, and what you're trying to prove is that if there is any error, the error is bounded or the risk is limited below what, with a certain confidence interval, would cause the election to change winner. In a typical election, this might require touching tens, maybe hundreds of ballots. But as the margin of victory gets smaller, the sample size needs to increase because you're looking for smaller and smaller error rates. So in the state of Georgia, they did an RLA on their presidential race. The margin of victory was 0.25%, and that would have required them to touch something around 10% of the universe of ballots. At that point, it's easier just to touch all of them, and so that's what they did. But broadly speaking, it's a random sampling process that mitigates malicious software. So how do you make this even better? Well, one of the interesting inputs to an RLA is that you need to know the margin of victory. I just told you that if there's a large margin, you need a small sample. If there's a small margin, you need a large sample. How do you get the margin? Well, what if the very computer that's telling you the margin of victory is itself lying to you? That could be because the computer had malware on it. It could be because the election officials were not telling you the right thing. And of course, if you can arrange for there to be a very large margin of victory, you make the sample size small. And that makes it easier to do some sort of sleight of hand trick where you might try to forge the entire process of the risk limiting audit. So we want to use a cryptographic mechanism that allows the election officials to commit to lock down every single ballot before they start the audit in such a way that helps them prove, in a cryptographic and statistical sense, to prove that they're not cheating in the election. So what I'm going to be talking about today is an implementation of a design idea that was first explored a year ago in a research paper. So from research paper idea to implementation in a year flat, and that's what I'm about to be discussing. So let me tell you a little bit of the cool stuff that we're asking from the crypto system that we're using. So we're using what's called end-to-end cryptography, but that phrase is a little bit broad. The particular feature that we're very excited about is something that's called an additive homomorphism. So what that means is that you have typically a public key crypto system. We're using El-Gamal, and it means that you can encrypt two numbers, and then you can take these two encryptions and you can do something else to them. And it's the same as if you decrypted, added, and re-encrypted. But because it's a public key crypto system, Anybody can encrypt and anybody can accumulate, but only the election officials can decrypt. So we're giving an operation on encrypted numbers that any observer of the election can compute. And that means that anybody can recompute the totals of the election. And then, of course, only the election official can decrypt that total, but they can prove that they did it correctly. And how do you make a proof? Well, you do a thing called a non-interactive zero-knowledge proof, or NIZK for short. So every single one of those 0 or 1s, every bubble on the ballot turns into a 0 or a 1. And when you encrypt it, not only do you have the encrypted number, you also have a proof that that thing that I just encrypted is either a 0 or a 1, but you can't tell which. And in fact, you can even do that over a sum of all of the bubbles for a particular contest. So I can prove that every ballot is well formed. There was only at most one vote for president in all of the choices that were available to the voter. So any observer of the election can prove that there's no weird ballot stuffing in a cryptographic sense of trying to encrypt a really large number for your favorite candidate. The same mathematics also allows an election official to do what's called a decryption proof at the end of the election. They can prove that when they announce the totals, that the announced totals are consistent with the encrypted sum of all the encrypted ballots, which again, anybody can recompute. So what this means for a risk-limiting audit is now our election officials can prove to any observer that they are announcing the correct margin of victory, that they're not playing any funny business with that. And in fact, during the risk-limiting audit, when they roll the dice and they select specific ballots to be audited, that means those specific ballots will be physically located in a box on a shelf somewhere and then compared to an electronic copy. We're also going to decrypt those specific ballots, once again providing a high degree of assurance that the physical paper and the electronic copy in the server and the encrypted copy that was on a public web server all match up. All of that happens. So the randomly selected ballots will be decrypted as well and then posted for the public to see. All of this cryptography, so anybody who's ever thought about using cryptography in their code has been told, lesson number 1, first thing you do, don't build it yourself. Use somebody else's cryptography because it's hard to get it right. In this case, virtually all of the cryptography that we needed comes to us from a project that Microsoft started just over 2 years ago, I think, called ElectionGuard. And this was a general purpose software development kit that had all of the bits and pieces that we needed to implement this auditing strategy. And it happens to be open source. It happens to be in Python. And oh, by the way, I helped write it. So I know pretty well how it works. And so that was how we began building Arlo E2E, was on top of ElectionGuard. Doing this as a single core, single threaded task was easy. I had the thing running in a couple months with all the features I needed. And in fact, it wasn't even that much extra work to port it to use Python's multiprocessing library. And then my 6-core desktop was running 6 times faster. Easy. So, hey, if I can do that, I should be able to easily make it run on a giant cluster of thousands of machines, right? Well, so let me give you some of the numbers. The paper ballots go through a high-speed scanner, maybe not this specific one, but something that looks a lot like it. And every ballot gets imprinted. There's a printer inside the scanner that stamps a little number that's unique on each ballot. You don't typically want to have unique numbers that are visible to the voter, but you do want to have unique numbers so that way you can associate some electronic version of the ballot with a very specific piece of paper that it came from. Well, that scanning process, when it's done, gives us a gigantic comma-separated value file. So if there were 100,000 ballots, there's 100,000 rows in the CSV file, 1 row per ballot. Now, the encryption is actually astonishingly slow. So encrypting a typical ballot for a typical election on my desktop machine, which happens to be a 3.5 gigahertz Xeon, takes roughly 6 seconds. That's a long time. And it generates about 1 megabyte of JSON data that is then written to disk per ballot. And you run a profiler, and big surprise, the bottleneck is the modular exponentiation that's at the root of generating the proofs, generating the encryption. All of the math that you're doing is all 4,000-bit numbers raised to 200-something bit powers. And that's very expensive. So you might say, oh, well, you should optimize that. Well, we're using GNU multi-precision, which is already hand-tuned assembly code for exactly this. So we're not going to micro-optimize our way out of this problem. Instead, in order to scale, we have to run on a cluster. So a reasonable performance target might be 500,000 ballots per hour. So here's some numbers I grabbed from the last election. In Denver, Colorado, there was roughly 400,000 ballots. In Seattle, Washington, there was roughly 1.2 million ballots. So I want to be able to generate all of the encryptions and proofs and everything for one of these elections in give or take an hour or two. Like, that's acceptable. Start it, get dinner, come back, it's done. That's the kind of performance target I have. You do the math, that means I need to run at about 140 ballots per second. And assuming I had perfect scalability, and we know you never ever do, I would need about 1,000 cores to do it. This is totally CPU bound. I'm not going to run into network issues, I hope. And it should theoretically parallelize very well. What could possibly go wrong? Well, I'm going to need a cluster library. And what are my engineering constraints? Well, it needs to work easily with Python, because ElectionGuard is in Python, my auditing tool is in Python, so whatever I'm doing, it has to be Python. And my job looks a lot like a MapReduce job of exactly the sort that Google popularized for cluster computing in the early 2000s. So the map is I need to go from a plain text ballot to an encrypted ballot. And I need to do this map across a list of 100,000-ish ballots or more. And then the reduction is I need to compute the encrypted sum of all of those ballots. So I need to, whenever I have two, I'm going to use that additive homomorphism to let me combine the ciphertexts and eventually get down to a total for every single contest, for every single race. So any MapReduce library that understands Python ought to be able to do what I need. But I have other issues too. One thing is that portability matters. I happen to be developing it against Amazon, but I want it to run on Microsoft Azure. I want it to run on Google Cloud. I don't want to lock myself into a specific cloud. And my expertise is in security and a little bit of crypto and a little bit of elections. I am not an expert in cluster scalable compute. I don't want to have to worry about allocating nodes, scaling, worrying about setting up the security permissions just right for all of the nodes to talk to each other, but not anybody else. I want to be able to just say, make me a node, make me 1,000,000 nodes, go run, I don't care. And of course, that means that I know from the get-go that I'm going to have engineering challenges and I'm going to need help, because you always need help. And so having an active developer community matters a lot. And even though I haven't written one line of the cluster parallel code yet, I know that there's going to be more to it than MapReduce. Somehow, somewhere, I'm going to need to do other kinds of things across my cluster, so a general purpose library would seem to be a useful thing to have around. So you take all of these constraints, and Ray jumps out very early as one of the obvious choices. And so I talked to some friends, and they said, yeah, you should give Ray a try. So all right, what happened? So I'm going to talk today about some lessons that I learned while taking my simple code that ran just fine on my local machine and making it run on a giant cluster. So let's start with the lesson that everybody knows is true, but you don't really recognize it until it hits you in the face, which is that your scalar performance matters. So initially, I was using Pandas, which is a popular data processing library in Python, to read my comma-separated value files in. But I needed to do some pre-processing on the data to figure out what the ballots looked like, to figure out what contest was in what ballot style, that sort of thing. And I wasn't sure how to make Pandas do it directly, so instead I just sucked the data out and iterated over it, leading me to a very common mistake in Pandas, which is using a thing called iteros. So common that you can find lovely web pages like this saying, for the love of God, don't do exactly the thing I just did. So what did I do to fix it? Pandas has a bunch of built-in operations that are hand-tuned and very, very fast. If you want to just add columns up, Pandas can do that much more quickly than you could do it in your own code. So, but I don't want to add them per se. I want to check how many have something and how many don't have something. So here's what that code ended up looking like. This is the only line of code in my talk today. So this piece says, please give me all of the rows where the ballot type happens to match some value that I'm searching for. So now I get out some subset of my database. And then, excuse me, I'm asking for, give me all of the fields that are not empty. One of the interesting things that Pandas does is it gives you a floating point, not a number, for any blank cell. Well, okay. So if it's not a number, make it true. If it is not a number, then make it false. So then, once I've got that, I can add those. True acts like a 1, false acts like a 0, and this lets me count all the non-empty cells in a given column. Doing it this weird way, which is not natural to write and takes a while to figure out, gave me a 10x performance boost over my handwritten Python code. And if I really need it later, I don't need it yet, but there's a nice library called Modin, which is API compatible with Pandas, but does all of this over array cluster. I don't need it today because I got such a big performance boost just from the scalar optimization. But if I do need it, it's there waiting and might even just work. We'll see. Second rule, of course, is to do as much in parallel as you can. So originally, I thought that the crypto was so expensive that everything else I could just do on the head node, no big deal. So when you convert from a row of CSV into the data structure representing a plain text ballot, that data structure is actually a fairly complicated series of nested Python classes. There are elections that have ballots, there are ballots that have contests, there are contests that have selections, and constructing that whole hierarchy actually takes real compute time. And that actually mattered. It slowed things down visibly. So my solution was just to pull out the basics from my Pandas data structure, in this case saying, give me a list of Python dictionaries. And then once I have all of these records, I just sent those out to the remote nodes. And I built my complicated hierarchy for my plain text ElectionGuard ballots on my cluster rather than on the head node. And that actually had a real significant performance bump. The other thing that everybody tells you, but you don't know it until you run into it, is even though you think that your compute bound and data transport isn't going to be the thing that matters, it's still a thing that matters. And so I even sort of guessed that this was going to be an issue. But still, in the beginning, I said, right, my task is encrypt a ballot, return the encrypted ballot. Well, I mentioned that an encrypted ballot is a megabyte. And if I'm doing this across a universe of 1 million ballots, now I have, gosh, 1 million megabytes. Ew, I don't want to deal with pushing that kind of data around through my cluster if I can avoid it. Here was the architecture I settled on after a bunch of trial and error. That I would push 4 ballots at a time. I called that a shard. I pushed 4 ballots at a time to a remote task. It would encrypt all 4 of them and write them out to S3. I just use S3FS fuse, so I get a local file system, so I don't have to think about it too much. I would write the encrypted ballots out to S3, and then I would add them right there where I just encrypted them in the first place. And then I would only need to return just that one partial sum. So for n equals 4, I generate 1/4 of the data traffic, because the only thing I need to return for any subsequent compute in my cluster is those partial sums. The encrypted ballots I have dumped out to S3, I'm done with them. And oh, by the way, when you're writing to S3 from a whole bunch of nodes in the cluster, S3 knows how to scale with you. Amazon deals with that problem. You don't have to worry about it. So I'm able to get a lot of aggregate bandwidth onto my file system, and I don't have to deal with bringing that all back to my head node again. And oh, by the way, doing this exact same thing just on my local computer, I got about a 2% speed up, probably from overlapping I/O and compute. So in essence, I got a big win doing part of what would have been a separate reduction phase inside of my map phase in my MapReduce computation. Data lifetime also turns out to matter, and this was subtle. I didn't understand this at the beginning when I first was working on this. So originally, I would start all of my encryptions. I would say launch them all, just do a Python list comprehension, and I get back the list of object references that, of course, haven't all been computed yet. And then I would immediately start generating the tally structure to add them all up. And what that means is the distributed object store, which if you're using Ray, that means it's Plasma. Plasma needs to hold on to some of that data for a long time. If it takes 2 hours to do all of the encryption, that means that I have object refs that are living for 2 hours. Or if it takes 30 minutes, they're lasting for 30 minutes. But that's actually a problem. You want to minimize how long these object references need to live. The longer an object reference lives, the more pressure there is on the object system. And of course, as the problem set size grows, now the pressure grows on the object system. So the way and this, by the way, caused some really hard to debug crashes. The solution was that I broke my long list of ballots down into smaller batches. Every batch in this case was 10,000 ballots, and then I separately would launch them one batch at a time. So I would say encrypt 10,000 ballots, tally them, and get back a single partial tally. A batch on my cluster was running in 2 to 3 minutes. And then I would have back just a single partial sum, and then I would launch the next batch. And then I'd get back another partial sum, add those, etc. What this means was that between batches, the amount of data that I'm keeping live on remote nodes is none. I'm done with all of that. And that means that my memory use grows and then falls down, grows and then falls down. And it's no longer dependent on the problem size. I can always just add more ballots and it'll take longer to run, but it won't beat up the memory system any further. The last thing I want to talk about is making my reduction phase faster. My initial tactic was to build a fat tree. So like every node in the tree corresponds to adding up 10 children. And so at the bottom, I would have, whatever, 1 million ballots. And then I'd have 100,000 nodes. And then I'd have 10,000 nodes, 1,000 nodes, 110, and then one root that represented the sum of everything. And I would build this big task that depended on other tasks that depended on other tasks. It was sort of cool if you're like a functional programmer thinking about lazy evaluation, but it was a terrible strategy in terms of object lifetimes, because it meant that that root node had to wait for all this other compute to finish, and that has scalability issues. My new tactic, what I'm doing today, is, again, one batch at a time, 10,000 ballots at a time. I call ray.wait, saying, let me know when you have some results. And I do it with a relatively short timeout. And so as I get partial results back, then I dispatch more tallies. So results come in, I say add them and send it back out again. So this means that my object lifetimes are very, very short. Now I'm taking advantage of the fact that the addition that I'm doing over these encrypted ballots is both commutative and associative, which is to say ordering doesn't matter. You always get exactly the same sum. So I'm really taking advantage of the commutativity and associativity in order to do this out of order, because I don't care about order. I care about speed and I care about minimizing object lifetimes. And by doing it in smaller batches, ray.wait, if you say wait on 1 million object refs, I was told don't do that. That's not going to work. So keeping a smaller working set size really speeds this up. And last thing I want to mention is ray actors are fantastic. This is the thing that I didn't know I was going to need until I needed it, and then there it was for me. So actors are a way of encapsulating global state and being able to send messages back and forth to those actors to update that state. So I ended up using actors for 3 separate tasks. One is I used actors for my progress bar, because I wanted, if something's going to run for 2 hours, you want to watch it making progress. You don't want to get far along and have it just crash and you don't know what happened. So I built a progress bar actor where all my remote nodes would phone into it to say, I finished one, I finished one. I also am writing all these files to disk. I want to keep track of which files have been written, and I need to keep track of their hashes, because ultimately I need to be able to publish a root hash of all of the file hashes, because that's how we do data integrity verification later on. So that's just another actor that's collecting a giant dictionary that maps file name to hash. No big deal. The last thing, and if any of you in my audience know how to fix this, I would love to hear about it. Sometimes you write to S3 and it fails. Why? I don't know. But 1 out of a million writes just seems to fail. So I built a whole infrastructure to do retries, and then I have to keep track of pending retries. And so I have an actor whose job it is to hang on to all of the pending write retries, so that way I know when I'm actually done. If somebody has better fix for this, please help me. That was really a total hack. All right, caveats. Lessons I've learned that I think would be valuable to any observer, to anybody writing their first Ray program. So I come from a world of static types. I'm normally using programming languages like Java, but this time it's Python. So of course, being a static type head, I'm using MyPy everywhere, and I have type annotations all over my code. I really want to have MyPy catching my bugs before I even try to run them. Well, Ray doesn't use that yet. So there are a lot of places where I thought I had an object ref to X, and what I really had was just an X, or vice versa. I ended up filling my code with if is instance something, then error. And once I got it right, I was deleting those bits. So do be careful with Ray when it doesn't do it doesn't play nicely with MyPy yet. I hope they fix that. But a more important thing is that don't use every crazy Python feature. So it turns out that default parameters don't work on remote methods. I tried and I was getting weird errors, and the answer was don't use default methods. If you build a wrapper if you want one, and then the wrapper calls your remote method. I will say that vararg functions worked great, and I used them all over the place. Serialization of complex data structures also turned out to be tricky. The ElectionGuard Python library was being really sophisticated with Python class constructors, post-init methods, all sorts of stuff that just didn't serialize properly. And so I had to go in and hack my way through ElectionGuard Python to unsophisticationalize it in order to make it play nicely with serialization, so that way I could be passing these things back and forth between Ray nodes. Even GMPY2, which is the Python wrapper on top of GNU-MP, I had to write custom serializers. But if you take nothing else from this talk, it's scale gradually. First I did 100 ballots, then I did 1,000 ballots, then I did 10,000 ballots, then I did 100,000 ballots. And every time I multiplied by 10, something broke. And so if you do it gradually, both scaling up your problem set size and scaling up your cluster size, you will be able to back off when things go weird and figure out what went wrong. So I have a quick demo video. I don't trust myself to do a live anything with this, but I'll give you the demo. So on the left is my terminal window where you see the encryption happening. On the right is the Ray dashboard. So we are 27% into a job here. You can see that a message gets sent to my progress bar every time a ballot is encrypted, and it's chugging along pretty nicely, way faster than my desktop computer would ever hope to go. You might pay attention to this number at the bottom. That's the total memory usage across the full cluster of Plasma. So right now it's hovering around 630 megabytes. It eventually gets up to a gig and then drops down at the end of the batch. End of the batch? Yeah, so you can see right now we are rapidly approaching 30,000, which is a magic number because my batch size is 10,000. And you see that we have stragglers. And as the stragglers are slowly completing, If you look down, you'll see the memory usage of Plasma is growing. Plasma is up to 917 megabytes. And finally, our last stragglers are going to be finishing just in a second or two now. And boom, we're done. And you'll see the memory usage is dropping. We're down at 500. We're down at 206. So this is the batch structure of my job, keeping my memory usage in control. All right, so where are we today? We used this in our very first pilot election, which was Inyo County, California, just a month ago. The map shows Inyo on the right. You can see that Inyo is on the eastern side of the state. And Inyo, by the standards that I was engineering for anyway, was a relatively small election, only 9,628 ballots. But I had some people watching over my shoulder on Zoom when I was running the encryption, and the whole thing ran in 3 minutes flat. It took more time to explain what was happening than to actually watch the compute run, which is exactly what you want. And this was the first ever verifiable risk limiting audit. So that's kind of cool. I'll tell you that all of the code behind this is open source, so you can go check it out on GitHub. The URL is on your screen. And for those of you who aren't doing anything involving elections, don't panic. There's still some useful code in here that you might want to borrow or be inspired from. You'll find a file called rayprogress.py, which is my general purpose progress bar actor, and it wraps TQDM, which is a popular Python library for doing progress bars. Likewise, my out of order reduction code is in rayreduce, and I actually have a whole bunch of ideas for how to get rid of that straggler problem and still keep it scalable. If any of you want to hack on this, I have some ideas, and I could see some fun collaborations, and we could make this into a general purpose library that doesn't need to be part of Arlo E2E at all. If I've whetted your appetite for the interesting world of end-to-end voting cryptography and you want to learn more about that, well, at the bottom of your screen is a link to a YouTube video of an hour-long talk I gave at Dartmouth a couple years ago, and there are several other ones online. That's not really what today's talk is about, but there's a lot more depth and interesting things in the world of election cryptography. And at this point, I'm going to wrap up, and I want to say that this was work that has been built on work that's been built on work that's been funded by a number of people over the years, including the National Science Foundation. I definitely want to give a shout out to VotingWorks, the not-for-profit where I'm doing my sabbatical this year, and to Microsoft for helping make ElectionGuard happen. And at Anyscale, I need to give special props to Bill Chambers and Sang Cho for answering my questions and Zooming with me and watching over my shoulder when things broke and I didn't understand why. And at that, my talk is done, and I think we're going to move to questions. So thank you very much.
Hey, thank you so much, Professor Wallach. Super interesting application of Ray. Any questions from the attendees? While we wait, Professor, I have a question. So it seems the nature of the computation has a lot of numerical computations. Have you tried GPU for acceleration?
Yeah, so this would be amenable to running on a GPU. This would also be amenable to running on an FPGA, where if you say, I would like to have a 4,000-bit multiplier, please, well, if you have the real estate, you can have the multiplier. That kind of engineering is also hard to do. And if I was going to be running this 24/7, then it would make a lot of sense to invest the effort to make it run on an FPGA or a GPU. This is something, however, that's going to run once or twice a year. And the notion of allocate a big cluster on Amazon or Azure or Google for a couple minutes, run a big job, and then tear it down, that's just fine. As long as I can hit my performance target, I'd rather not do all that extra engineering. I mean, yeah, I could. But if I don't need to, I'd rather not.
Thank you. I think there's a question from the audience. Okay, there's a comment from John. Thank you, John. Said, thanks, Dan, a really interesting and enjoyable talk.
Yeah, so please feel free to type your question into the Q&A. I can read it, and I'd be happy to answer more questions.
Yeah, I do have another question. So it seems you have you have to spend effort on tuning some quote unquote magic numbers, like a group of 4 ballots at a time. So what utilities do you think could have helped?
So a lot of this, I mean, the map reduce is such a common paradigm that it makes a lot of sense that Anyscale can and should build a general purpose MapReduce library, and it can perhaps auto-tune those variables. You know, these are just things that I kind of did back of the envelope. Like, how did I pick 10,000? Well, 3 minutes seemed like a reasonable number for a run between batches, but you know, I don't know. I mean, as the Anyscale developers make ray.wait work better, they might be able to go to bigger batch sizes. And that would be a thing where that functionality at some point should get sucked into the core ray library. And then as the ray library improves, the tuning can change.
I see. So I know there's a question from Huey, but super quick follow-up. Which version of Ray did you use?
Which version of what?
Ray. Which version
Ray.
of Ray?
So I started when, you know, before they had the 1.0 release. So I started with 0.87. Then for a while I was using the daily build. Right now I'm on 1.0.1. I've had a lot of back and forth as I've found interesting bugs, and sometimes my fixes have shown up on the nightlies and then they get folded back in. So it's been an interesting relationship, and I'm actually very happy with the level of support I've gotten.
Thank you. Thank you. Yeah, there's a question from QE.
Should I take the question that's typed here?
Yes. So the question from Simba is communication between read nodes also secure?
So the communication between the ray nodes is as secure as an Amazon EC2 enclave is. And this is exactly the kind of place where I'm not an expert. You know, writing IAM policies for Amazon is not my idea of a party. They're very easy to get wrong. So I know that when you use the Ray autoscaler builds all of the security infrastructure around your cluster to make sure that the cluster nodes aren't externally accessible. I hope that Ray gets that right, and I hope that that's the thing that I don't have to worry about. What I will say is, fundamentally, I'm pushing plain text ballots up to a cluster to run the compute. So that means that that plain text exists in the cluster while the compute is running. But then when the compute is done, the cluster nodes are deallocated and they go back into Amazon's pool. And I'm sure that Amazon does a pretty good job of zeroizing them. They really have to. Otherwise, we have a way bigger problem. The other thing is that everything that I write out for the long term, I write it out to S3. And everything I write in S3 is public. Like, the buckets are public. You can mount the buckets yourself. It's also exported through their static web service. So the long-term things that are the outputs of the compute are safe for the public to read. And we use hashes to help protect them from tampering.
Thank you. Yeah, there's an additional question then about adoption in other elections, this technology.
Well, obviously, VotingWorks is a not-for-profit whose job it is to build technologies that are used in real elections. VotingWorks helped run risk-limiting audits in 9 states, and they also build voting machines that were used in the state of Mississippi. And they have their own plans for expanding over the next couple of years to have a larger share. And this is VotingWorks code. And I hope that this will be a feature of many election audits to come in the future. We piloted it this year, and over the course of the next couple of years, I hope to see this more broadly used. And you know, you got to start somewhere. We started with 1 election, and over the next couple of years, who knows, maybe this will become a standard thing. We'll see.
So related, Dan, so do you plan to return to Rice University after 2020?
Well, For the non-academics in the audience, when you go on a sabbatical, you go back to your home institution for a year after your sabbatical. Like, that's contractual. Otherwise, you have to like pay them back. So I'm definitely going back to Rice for the next year. And part of the fun of being a professor and part of how you keep the job of being a professor fresh is that you take these sabbaticals and you go visit the real world, and then you learn things about the real world that don't happen in the ivory tower, and then you return hopefully smarter and rejuvenated and all of that. So this is sort of the usual thing that every professor does. Some people take sabbaticals and go start companies. I took a sabbatical and built some election technology.
Thank you. This is very meaningful work.
Yeah, I have a whole bunch of ideas for how I'm going to make the Rice security class students build some kind of an exercise around this code. Exactly how, I haven't figured it out yet, but if I spend a year working on this code, I can find a way to make a 3-week class project on it. The students are going to love that.
Yeah, look forward to that. Okay. Yeah, thank you so much for tuning in. And yeah, thank you so much, Professor Wallach, for spending your time. Yeah, I learned a lot. And yeah, we hope to improve Ray to serve these kind of applications better. All right, thank you. I think, yeah, that's it for our presentation today. Thank you so much, everyone. Yeah, hope you have a nice one.